Today we're going to talk about sizing brake resistors. You should be seeing the Bonitron building on the screen right now. Well, in case everyone here hasn't been there, this is the Bonitron building. We've been in Nashville, Tennessee for around 62 years. At this location for around 30. Right close to downtown. You can see the downtown skyline from the front of the building here. Started out as a government contracting house here, and then we moved on to VFD accessories, starting with DuPont in the 70s with our ride-through products. Still one of our, still our number one product today is our ride-through product. All of our standard products are designed and manufactured right here in Nashville. We have two locations now, the one that you were just seeing there, close to downtown, and then we have another location located out in Laverne, Tennessee. Our different products we cover here in families are over voltage products, handling rise in the DC bus, and our green, our solutions, our Regen, our 3800, things that allow you to recycle the rise, the Regen energy. We also have some maintenance products like our cap formers, our under voltage, and one of our largest product families we cover here is our common bus solutions, linking up multiple drives and giving you one solution there for multiple drives. What we're going to cover today is braking techniques for AC drives and how to size braking resistors specifically. Most all of our products that we cover here are going to connect to the DC bus of the variable frequency drive. Our transistors in this specific presentation is what we will talk about connecting to your DC bus. In some occasions, you have drives with a 7th IGBT. In those occasions, then the resistor would just connect directly to the brake resistor terminals that are normally BR1 and BR2, positive and negative, or just BR1 and BR2. Most resistors don't even have a polarity. The typical parameters for 460, 480 volt AC line, DC bus. The DC bus normal operation is normally at 640 volts DC for 460 and 670 volts DC for 480. Also, I forgot to mention, we have here with me today Tim Watkins. He's our tech support manager and the guy who really helps me do a lot of the more technical sizing here. He will be chiming in off and on and giving us some specifics in some portions of the presentation today. Our typical set point for our 460, 480 volt AC line brake choppers going to be at 750 volts DC. And all that simply means is that at 750 volts DC is when this unit is designed to cut on. So when your DC bus rises to that level, the chopper will cut on and send the excess voltage over to a resistor. Get a lot of questions, or people that call in that might just ask for a resistor, don't even understand that really the transistor is the brains of the operation when you're dealing with dynamic braking. So if you don't have the chopper inside of the 7th IGBT inside of your variable frequency drive, you're going to need to purchase an external transistor or chopper. Or if the load is considered too much for the 7th IGBT, you might need a heavier duty external chopper. Most drives you can enable the internal IGBT and use an external chopper in those cases. You will need to consult your various drive manufacturer for your overvoltage trip point on your drive. Your standard that you see is normally 800 volts DC for a 480 volt line. but you do see a lot of the servo systems or multi-axis systems where they have much lower set points, something like a 730 or something like that. In those occasions, you it does not mean that you can't purchase an external chopper to handle this. We just need to be notified. We can do custom set points. We will get into your regenerative energy profiles now. What this is concerning is the overvoltage profile, meaning the power curve that you are receiving on your DC bus from your load. And so I know it's not a curve, but this would be the curve. This is for a deceleration cycle. You hear a couple different terms when it comes to duty cycle in resistors. You hear decel and you hear overhauling. A decel is exemplified by this right here, where you have a high peak and then it's followed by the over voltage going down consistently. This would be a decel cycle. So your braking power, your max braking power is right here by your peak, and then once you reach your peak, it's steadily decreasing. And that is where you get your decel. Okay, and then you will have this is your time braking, and then your time in between your braking, the beginning of the brake, and to the next brake is your cycle time. So if it brakes, then you have 5 seconds in between here. In between your next braking or regen occurrence, then that will be your cycle time in a decel cycle. Most of your decel cycles that you see are going to be handled by a lighter duty resistor, a 10% duty resistor. This is not a heavy duty cycle. Unless it is happening a lot of times over a small period of time. So if it's happening every maybe 200 or 300 milliseconds or something like that, it can be considered as continuous for there, even though it's a small decel. The next energy profile that we will discuss here, excuse me, my computer's moving slow, is the overhauling cycle. And in an overhauling cycle, this is normally going to occur when you have a load that is constantly pushing the motor faster than it wants to go, like a downhill conveyor or such. So you really aren't having that decel at the peak. It is having a long peak here, and that is an overhauling cycle. So your peak lasts for quite a bit longer in the time braking, and then it instantly is cutting off here right after your brake. So it's the same thing goes for the time in the cycle on this one. The big difference here is, especially with the resistors, you want to pay attention to the overhauling percentage. Most all of Bonitron resistors are going to be sized to overhauling load. We are not, when we say a 10% duty cycle, we mean 10% overhauling load. There is a big difference in sizing. A lot of the resistors that you are going to purchase from most of your resistor manufacturers are not overhauling load. They are decel loads. So when they say 10%, they mean a 10% decel load, and that's a different thing, or a different percentage. A 10% overhauling load is true 10%. So if your resistor is rated at 1,000 kilowatts peak, then 10% overhauling load is 10% of the 1,000 kilowatt peak. All right. I will move along here, and I've already kind of discussed some different applications that will fit into the different duty cycles, but it helps a lot of people to understand that more so, because you might not deal with resistors every day and duty cycle and things in those terms, but most people, it depends on where you're at, you're dealing with different applications almost on a daily basis. So, so we will get into this. Cranes, as you see, are normally a 50% duty cycle, braking duty. And what you will see in a crane is a heavier duty cycle, meaning that is an overhauling load. You're dealing with a heavy load that is pulling the motor down faster than it wants to go during the decel time. So you're hitting the drive with a peak overload for a continuous amount of time, whatever that may be, depending upon the crane and the cycle. Downhill conveyor is the same thing. The load on the conveyor moving downhill, the inertia is pushing that motor in the same way. Where you get a lighter duty cycle, we see things like a conveyor, a flat conveyor that has a heavy load that's moving along. You're rarely ever getting a overhauling load on that, except when you go to stop or slow that load down. So when you slow that load down, it's going to get a heavy amount of regen back to the DC bus, but it's only going to be for a small amount of time. Once it reaches that peak, it's going to instantly start going down with the braking energy. And I'm going to bring Tim Watkins in here, and he's going to discuss a few slides here that he has some more technical issues. If you have some questions, feel free to type your questions in here as we go, and we will get to them.
All right, yeah, I'm Tim Watkins. I take care of a lot of the technical questions and write the documentation for the user manuals that Bonitron has on its website. Basically, going into the nitty-gritty details that Stuart has covered some of already. Sizing a brake resistor, basically, you have to kind of understand your application, understand the power requirements, and what your drive is capable of. A drive, that's rated for 50 amps cannot brake at a 200 amp current. It just can't. It will destroy the drive. And so what actually limits the current that you get out of a drive is going to be the resistance on your resistor, and that's just the basic Ohm's law, V equals IR. So the peak current that you're going to get is basically the we'll go into that a little bit later, but you just need to be aware of what your peak braking power is going to be. That's the voltage at which your braking transistor is going to turn on. Your peak current requirements, that's going to be key in sizing the resistor and wiring as well. Whether it's an overhauling or braking load, and the duty cycle that you expect to get on your resistor. All right, so calculating the braking horsepower, basically the peak output. Basically, Bonitron, unless told otherwise, we are going to rate it to what the drive output is going to be. So we basically size it for the heavy-duty load, and basically not knowing the customer's process or really being part of the system design, we tend to rate it rather conservatively and be on the higher side. So our peak outputs that we expect from a drive is going to be 150% of the rated horsepower of that drive. By rated horsepower, we just mean the nominal horsepower, what you expect to get out of the drive. So doing that, we basically calculate the current, basically using another version of Ohm's law, P equals IV, and we calculate out the current and what we expect the current to be for that resistor. V break here is the voltage at which the braking transistor turns on, and I've given this table on the right over here, basically based upon what your AC line voltage is going to be, what Bonitron's set point is for braking transistors. This is variable, and we can realistically set it to any voltage that you might like. But this is our normal factory set point, and this has been good across the industry. In fact, we get this from a lot of other drive manufacturers for these set points. So, and actually finding the resistance required, we basically can calculate out, Ohm's law once again, and be able to find the value for R to get the expected peak current and solve for that. But once you have the peak horsepower, you just need to size your resistor based upon that. And the next requirement is going to be the duty cycle. Stuart's talked briefly about this a little bit, but basically it's just the time you expect to be decelerating or slowing the load down from a higher RPM to a lower RPM. Basically, you're going to take that time and over the entire time of the cycle. The important thing is that the deceleration time just should not be over 50 or 60 seconds, otherwise we'll consider that continuous. An example would be if you're decelerating for 2 minutes out of a whole hour, it's a very low duty cycle overall, but realistically with the resistor heating up, the resistor will get too hot during that 2-minute braking time, and Bonitron will just consider that a continuous braking application. So here's a few equations basically talking about how we rate the continuous power, and basically it's just the peak power times the duty cycle. So if it's a 20% duty cycle, that's going to be overhauling, it's just the peak times 0.2. But if it's braking, we assume that it's braking linearly, and so we just divide that same value for the overhauling value by 2. And that way you can calculate how much, basically how much power the resistor needs to be able to burn out. This is a lot more detail on this page than most applications will probably need. But if you do have customers that are very, very curious as to where some of these values come from, basically I've taken some torque calculations and how you can calculate the torque that you're going to get out when you try to slow a drive down from a higher RPM N2 to a lower RPM. And from there you can take that and get an accurate measurement of the power of that time. And if you really want to, you can solve for the total power and get the total energy out using a bit of calculus. But that's really not required. What's really required is just basically what your expected duty cycle is going to be and your peak horsepower is. And make sure that your resistor that you choose can be sized for the current. Our salespeople are trained in how to do this, and I understand you don't deal with this every day, and Bonitron does, so we're quite good at sizing resistors just based upon the horsepower of the drive and our knowledge of the application process.
Well, there's one more thing that I want to go over that I did not touch before we close out, because we get quite a few questions, especially if you're a distributor, integrator, or anything like that, and you're dealing with different things in the field. Give me 1 second here. And it's pertaining to the ohms of your transistor and your resistor. If you go to your drive manufacturer and you look up the models, they should have a manual somewhere with minimum ohms for their braking transistors. I will show you what to go through for the guidelines for Bonitron. For Bonitron, the main thing that you want to pay attention to, because you run into customers who have a resistor that's blown up, or they might call you because they're having issues all of a sudden with a DC bus overvoltage fault on their drive. and they're not used to having it. And you come in there and you've never dealt with their drive or their system before, but you're trying to apply a resistor to that. If they do have the 7th IGBT in the drive, then, like I say, you will want to either contact the drive manufacturer or try to find the manual that shows you the different minimum resistance allowed. Now, the minimum resistance allowed on the transistors, that simply means you just can't go lower than the value shown here. So for instance, our 30 horsepower lighter duty cycle transistor has a minimum resistance of 25 ohms, which is clear to see right here. We try to make it easy for you here at Bonitron to just go directly over. If you see braking resistors here, or M3775 arcade braking resistors, and you look here for the 30 horsepower, if you see, like I said, 10% overhauling load, you should see ohms for the 30 horsepower, 25 ohms right there. So that is one guideline that you really want to use. Anything higher than that can be used. You know, you get a lot of times they need something fast, you need to get it quickly. We can use a higher ohm than that to fit things into. But you would need to know, like I said, we would need to figure out what is their peaks, or how often are they getting this over voltage fall for those occurrences. That's one of the last things that I just wanted to say before we closed out, because it's very important, and it's one of those things that I think is kind of misunderstood, but it makes it more simple when you know. Just simply look on that for your drive or for our external transistors, and it can help you match up the resistor to what you need. You'll just have to go through and find the duty cycles that you need. For anything that you have, though, feel free to give me a call here. I'm pretty familiar with almost every application. If you can give me the times or the cycle time, then I can help you find what you need to find. I hope this has been helpful for you. If you have any questions, feel free to send us an email here. And that's all I have. You all have a good day.